Is a rocket really the only way to reach space? What if there are other alternatives? First, let's ask a more basic question. Why is getting to space so expensive? Because rockets are not just lifting cargo. They also have to carry their own fuel. And to carry that fuel, they need even more fuel. So from the very beginning, the system is fighting its own weight. That is why sending cargo to space is one of the most expensive logistics problems humanity has ever faced. During the space shuttle era, the cost to reach low Earth orbit was roughly $54,500 per kilogram. Newer commercial systems have reduced that number dramatically, but access to space is still expensive, complex, and energy-intensive. That is exactly why engineers have been asking the same question for decades. Could there be another way to reach space without relying entirely on rockets? And the surprising answer is yes. In this video, we are going to explore 7 major alternatives to rockets. Some sound completely insane. First concept, the space elevator. When we want to go up a skyscraper, we do not strap on a jetpack. We use an elevator. So what if reaching space worked the same way? Not with an explosion, but with infrastructure. A space elevator would be a giant cable anchored near Earth's equator and extending far into space. The key number here is 35,786 kilometers. That is the altitude of geostationary orbit. At that height, an object orbits Earth once every 24 hours, which matches Earth's rotation. So from the ground, it appears to stay fixed over one point. Imagine a cable reaching not just to that altitude, but far beyond it. If the cable extends past geostationary orbit, the outward pull on the upper part can keep the whole structure under tension. That tension is the secret. It means the cable could stay stretched, and robotic climbers could move up and down it. Instead of launching everything upward with explosive force, you build a permanent route to space. But here is the real problem: the cable. It would need to be tens of thousands of kilometers long, extremely light, and unbelievably strong. Not just strong in the normal sense, but strong enough to support its own weight over a distance longer than Earth's diameter. Steel cannot do that. Kevlar cannot do that. Most materials we use today cannot even come close. That is why the space elevator is not mainly a physics problem. It is a materials science problem. The math works, the engineering logic works. But the material we would need still does not exist at the required scale and reliability. So the space elevator is not impossible in theory. It is a real scientific concept waiting for a material strong enough to make it real. Second concept, the Skyhook. Imagine Rapunzel dropping her hair from a tower. Except this time, the tower is in space. And instead of climbing from the ground all the way to the top, you grab that rope at exactly the right moment as it swings past you. A skyhook is a long rotating tether already in orbit around Earth. It does not reach all the way down to the ground. That is important, because this is not a space elevator. A skyhook is different. It is a moving system. A rotating cable in space, its lower tip can dip down far enough for a spacecraft or payload to connect to it at just the right time. And that is where the magic begins. If the timing is perfect, the payload grabs onto the tether as it swings by. Then the rotation of the skyhook transfers momentum and energy to that payload and sends it higher. That is the whole trick. The spacecraft does not have to do all the work by itself. Part of the job is done by the rotating tether, and that is why the Skyhook is such a brilliant idea. It is not a full road to space, it is more like a moving handoff point. In theory, that could reduce the amount of fuel needed to reach orbit or move to a higher orbit. And if fuel goes down, cost can go down too. But of course, there is a catch. First, the timing has to be incredibly precise. You are trying to connect to a fast-moving, rotating cable in space at exactly the right place, at exactly the right second. Second, the tether still has to be extremely strong and extremely light, and not quite as extreme as a full space elevator cable, but still far beyond easy engineering. And third, when the Skyhook gives energy to the payload, it loses some of its own momentum, so it must be reboosted, rebalanced, or powered back up somehow. If the space elevator is like building a railway to space, then the Skyhook is like jumping up, grabbing a moving rope, and letting orbit pull you the rest of the way. Third concept, the mass driver. What if we just shot things into space? That is the basic idea behind the mass driver. And yes, it really is that aggressive. A mass driver is a launch system that uses electromagnetic force to accelerate a payload to extremely high speed along a long track. Think of it like a giant electric catapult. The energy stays on the ground. The launch system does the acceleration, and the payload leaves already moving at enormous speed. In theory, that could dramatically reduce the amount of onboard fuel needed. It could also make launches more repeatable, more automated, and maybe one day, much cheaper. But then comes the big problem: acceleration. To reach orbit, you need incredible speed. Low Earth orbit requires about 7.8 kilometers per second, and that is roughly 28,000 kilometers per hour. And if you try to reach that kind of speed over a short distance, the acceleration becomes brutal. That means enormous G-forces. Far too much for a human passenger, maybe too much even for delicate electronics, depending on the design. Then there is another problem, the atmosphere. If you launch something from the ground at extreme speed, the air will fight back, hard. You get intense drag, intense heating, and huge structural stress. So on Earth, a mass driver is difficult. But on the Moon, that changes everything. No thick atmosphere, much lower gravity, and suddenly, electromagnetic launch systems start looking a lot more practical. That is why mass drivers are often discussed for future lunar industry. You mine materials on the Moon, then launch them into space without using chemical rockets every single time. So the mass driver may not replace rockets everywhere, but in the right environment, it could become one of the most efficient ways to move cargo off a world. Fourth concept, SpinLaunch. But there is another version of the same dream. Instead of pushing a payload down a long track, what if you spun it inside a giant machine and then let it go? That is the idea behind SpinLaunch. You place the payload inside a huge rotating chamber. Then you spin it faster and faster and faster until it reaches extreme speed. Then at exactly the right moment, you release it. Instead of using a long electromagnetic track like a mass driver, SpinLaunch stores energy in rotation. It is the same basic ambition. Give the payload a huge amount of speed before a rocket has to do everything else. But the way it does that is completely different. A mass driver pushes. SpinLaunch spins. The payload is not just moving fast, it is being whipped around inside a giant mechanical system before release. Fifth concept, balloon-assisted launch. The idea is simple. Lift the rocket as high as you can with a balloon, then fire the rocket from there. That is the whole logic behind balloon-assisted launch. A high-altitude balloon carries the payload or a small rocket far above the ground. Not to orbit, not even close, but high enough to get above a large part of the atmosphere. And that matters, because about 99% of Earth's atmospheric mass lies below 32 kilometers. So when a balloon lifts the rocket to high altitude, it is not just gaining height, it is leaving behind most of the densest part of the atmosphere. And that changes a lot. When the rocket finally ignites, it starts higher in thinner air with less drag, less pressure, and less energy wasted in the first part of the climb. That is the scientific advantage. The balloon does not take you to space. It simply helps the rocket avoid the thickest part of the atmosphere before the real ascent begins. But of course, there are trade-offs. A balloon is not precise like a launch tower. It drifts. It depends on winds. It depends on weather. And controlling the exact launch point is much harder. Also, a balloon can only lift so much mass. So this is not a solution for giant heavy payloads. It is much better suited for smaller launches, scientific instruments, or lightweight systems. Sixth concept, laser-powered launch. This idea focuses on one question. What if the vehicle did not need to carry all of its energy inside itself? That is the core idea behind laser-powered launch. Instead of storing all the energy on board, you send energy from the ground to the vehicle. In most versions of this concept, a powerful laser is aimed at the craft from below. That energy can be used to heat propellant, transfer momentum, or support thrust through other engineered systems. And that changes everything. Because the vehicle is no longer dependent only on the energy it carries inside. Part of the energy comes from below while the craft is already moving. That is why this concept feels so radical. It does not change where you're going. It changes how energy is delivered. And in physics, that is a very big deal. But the engineering challenge is enormous. First, the beam has to stay precisely locked onto a very fast-moving target. Second, the atmosphere is a serious problem. Air can scatter the beam, absorb it, and distort it. So even if the laser is powerful, delivering that energy cleanly and efficiently through the atmosphere is difficult. Third, the system has to manage extreme power levels without damaging the vehicle or losing control of the beam itself. Seventh concept, nuclear pulse propulsion. One of the most extreme space travel concepts ever seriously studied. This idea makes the most sense after you are already in space. Not for routine launch from Earth, unless your goal is to get investigated for war crimes before you even leave the atmosphere. The idea is simple, at least in principle. A bomb explodes behind the vehicle. The blast hits a massive pusher plate. That impact pushes the spacecraft forward. Then it happens again, and again, and again. So the spacecraft does not ride one long burn. It rides a chain of explosions. That sounds insane, but the physics is very real. Nuclear reactions contain far more energy than chemical reactions. That means, in theory, a nuclear pulse system could move much heavier spacecraft much faster than ordinary propulsion systems. In theory, a system like this could make deep space missions more practical, and it could push massive structures through space in ways that ordinary systems struggle to match. But now comes many obvious problems. First, you are using nuclear explosions as propulsion. That creates serious political, environmental, and safety issues immediately. Second, the spacecraft itself must survive repeated nuclear shock. That means the pusher plate, the suspension system, and the entire structure must absorb blast after blast without failing. Third, even if the engineering works, the world may simply decide that using nuclear explosions for propulsion is not acceptable. So this is not just a physics problem, it is also a policy problem, a safety problem, and a civilization-level risk decision. If you enjoyed this video, don't forget to subscribe to our channel and hit that like button, and share it with the people you care about, so the light of science can reach everyone.